How did our sun begin? James Webb just looked into our star's childhood. For the first time in human history, we are peering into the ancient, hidden chapters of our own cosmic origins. Thanks to the groundbreaking observations from the James Webb Space Telescope, JWST, scientists have just made a stunning discovery, a glimpse into what our sun may have looked like as a baby star. This revelation comes through the study of Herbig-Haro 21, HH21, a brilliant, youthful star system bursting with energy and light in a star-forming nursery just 1,000 light-years from Earth. But what does a newborn star really look like? What was our sun like before it settled into the warm, life-giving presence we now orbit? The answers to these questions are finally coming into focus, and what we are discovering is both breathtaking and humbling. The power of Webb, peering into the origins of stars. Launched in late 2021, the James Webb Space Telescope represents the most powerful astronomical observatory ever built. Floating in the dark silence at the second Lagrange point, 1.5 million kilometers from Earth, JWST uses infrared technology to see through dense clouds of gas and dust that block visible light. With this cutting-edge capability, Webb acts as a cosmic time machine, allowing scientists to explore the earliest epochs of the universe, witness galaxy formation, and now observe the very birth of stars, including analogs to our own sun in its infancy. HH21, a star is born violently. One of JWST's most exciting targets has been Herbig-Haro Object 21, a violent, glowing jet of matter shot into space by a very young star located in the Perseus molecular cloud, one of the most active star-forming regions in our galaxy. At only 1,000 light-years away, HH21 offers an unprecedented window into the early life of stars like our sun. HH objects, named after astronomers George Herbig and Guillermo Haro, who discovered them in the 1950s, form when energetic jets of gas from a newborn star slam into the surrounding interstellar medium at hundreds of kilometers per second. These shockwaves create bright arcs and glowing knots of material that radiate energy and paint the cosmos with dazzling colors. And that's exactly what JWST has captured in HH21. Twin jets erupting from a central protostar, rich in molecular hydrogen, carbon monoxide, and silicon monoxide. Indications of a binary star system forming at the core. Evidence of a rotating accretion disk, hinting at future planet formation. Unexpectedly low jet velocity, suggesting a very early phase of development, an ideal analog for what our sun might have been like more than 4.5 billion years ago. What does this tell us about our own sun? By studying HH21, we gain direct insight into the dramatic and chaotic processes that likely shaped our own solar system. Scientists now believe that our sun formed within a similar stellar nursery, surrounded by a thick cloud of dust and gas, and underwent an intense period of energy release before settling into a stable main sequence star. Just like HH21, the young sun may have ejected powerful bipolar jets to expel excess angular momentum, developed a flattened accretion disk, rich with metals and ice, from which planets would eventually coalesce, generated magnetic fields that shaped its plasma flows and influenced the orbits of early celestial bodies. These observations help answer fundamental questions. How did the sun accumulate mass? What forces shaped the solar system's planets? Why is Earth positioned just right for life? Understanding this stage of evolution provides more than just historical insight. It's a key to understanding the processes that make planetary systems possible throughout the universe. Magnetic fields and cosmic sculpting. Magnetic forces are silent, but powerful players in the drama of star birth. In HH21, Webb has revealed twisting magnetic fields likely directing the twin jets as they emerge from the central protostar. These fields also shape the surrounding interstellar medium, help control the rate of accretion, and may determine the structure of future planetary systems. This mirrors processes observed in our solar system, where the sun's magnetic field not only creates sunspots, flares, and coronal mass ejections, but also sustains the heliosphere, a magnetic bubble that shields the solar system from harmful cosmic radiation. JWST's view into HH21 shows us a smaller version of this, In the earliest stages, a heliosphere in the making. Jets of youth, echoes of the cosmos. What makes the discovery of HH21 so profound is that it captures the universality of star formation. These jets, previously thought to be unique to infant stars, have also been observed in the cores of ancient galaxies and around supermassive black holes. This suggests that the physics of accretion and ejection are common patterns in nature, echoing across vastly different scales. Just as baby stars blow out material they no longer need, active galactic nuclei eject plasma into space in colossal bursts. The principle is the same. Matter condenses, rotates, heats, and releases angular momentum and energy, shaping everything around it. From dust to planets, the seeds of solar systems. Inside the swirling accretion disk of HH21, the JWST has found the raw materials for planet building: carbon, silicon, oxygen, and trace metals, the very elements that make up Earth and you and me. But it's not guaranteed that planets will form. The intense energy from the jets and the chaotic gravitational environment may prevent the disk from condensing into stable planetary bodies. Still, many stars like HH21 do go on to develop complex planetary systems, and this process, viewed in real time by JWST, is a cosmic factory constantly seeding the universe with the potential for life. The dawn of stars, the blueprint of the universe. With every new image and data stream from JWST, we are unlocking the deep time story of our own existence. The study of HH21 not only illuminates the mystery of the sun's early days, but contributes to a growing cosmic blueprint. Stars are born from turbulent clouds of gas and dust. Jets regulate angular momentum, carving out future solar systems. Magnetic fields guide both the violence and the beauty of creation. Chemical fingerprints left in the gas clouds reveal the recipes of planets and atmospheres. This is no longer speculation, it is observation. Why it matters? Our past, our future. Studying HH21 is not just about curiosity. It's about understanding our origins and, possibly, our destiny. As we unravel the mysteries of how stars form, how planetary systems emerge, and how conditions for life are established, we get closer to answering the greatest question of all. Are we alone? And if not, how common are stars like ours? Planets like Earth? Solar systems that can support life? The answers, it turns out, are hidden in the baby pictures of the universe, now made visible through the lens of JWST. Conclusion: a new era in astronomy. We are witnessing a new chapter in the story of astronomy. The James Webb Space Telescope is not just a telescope, it is a revelation machine, and its discoveries are reshaping what we know about the cosmic origins of stars, planets, and life itself. From HH21 to the farthest corners of the universe, every discovery brings us one step closer to understanding the vast, intricate, and beautiful forces that made our world, and perhaps many others like it. We are no longer just observers of the universe. We are witnesses to its becoming.